After getting the basic knowledge about input-output system, let's move to modes of input-output data transfer. Data transfer between the CPU and input-output devices may be handled in a variety of modes. Some modes use the CPU as an intermediate path, other transfer the data directly to and from the memory units. It's a transfer to and from peripherals that may be handled in one of the four possible modes. First is the programmed input-output. Second is the interrupt-initiated input-output. Third is the direct memory access, or it is called DMA. And the last one is the input-output processor, or IOP. Now, let's start with programmed input-output. In the programmed input-output mode, each data item transfer is initiated by an instruction in the program. Once the data transfer is initiated, the CPU is required to monitor the interface to see when the transfer can again be made. In the programmed input-output method, the CPU stays in a program loop until the input-output unit indicates that it is ready for the data transfer. Usually, the transfer is to and from a CPU register and peripheral. Other instructions are needed to transfer the data to and from the CPU and memory. Here, the input-output device does not have direct access to memory, and the data transfer takes place under the direct control of the processor. The processor has to check input-output devices continuously, due to which it is unable to do another task frequently. Hence, this method is inefficient and slow. So, let's take an example of input-output operations, which involves a keyboard and a display device in the computer system. There are 4 registers available, which are used during the data transfer operations. These registers are: first is data in, second is data out, third is status, fourth is control. A program that reads one line from the keyboard, stalled outward in the memory buffer, and also displays that word on the display. This is an example that explains the programmed input-output mode, in which the processor continuously checks a status flag to achieve the synchronization between the processor and an input-output device. We can see that the processor polls the input-output devices. Pooling. Pooling is also referred to as busy waiting. In this situation, when an input-output operation is required, the computer checks the status of the input-output device until it is ready, at which point device is accessed. It is sometimes also referred to as software-driven input-output. Interrupt-initiate input-output. An alternative to the CPU constantly monitoring the flag, each let the interface inform the computer when it is ready to transfer data. This model transfer uses the interrupt facility. In the meantime, the CPU can proceed to execute another program. The interface min work is keep monitoring the device. When the interface determines that the device is ready for data transfer, it generates an interrupt request to the computer. Upon detecting the external interrupt signal, the CPU momentarily stops the task it is processing, bunches through a service program to process the input-output transfer, and then returns to the task it was originally performed. At least one of the bus control lines should be assigned, for this purpose, known as interrupt request line. Whenever an interrupt request is initiated, an interrupt service routine is initiated. On the other hand, the processor must send an interrupt acknowledge signal to the device to inform that each request has been recognized, so that it may remove each interrupt request signal. Interrupt service routines are handled in the same way as of subroutines, but a subroutine performs a function when some running program called the subroutine interrupt. Service routine may or may not have anything in common with the current running program at the time interrupt service request is requested. These two are different programs, and can often belong to two different users. Whenever an interrupt occurs, information on the current running program must be saved. This information will be restored after the completion of interrupt request. The information that is saved and restored includes the condition called flag and the content of any registers used by the program or by the interrupt service routine. Saving the register content to memory increases the delay between the request for the interrupt being received and the processor starts the execution of interrupt service routine. This delay is known as interrupt latency. The device which requests for an interrupt sometimes identifies itself directly to the processor. After getting the request, the processor saves the contents of the currently running process and start executing the interrupt service routine. This kind of interrupts is called vectored interrupts. If the processor is currently servicing a low priority device, only then an interrupt request of high priority device will be accepted, but if the processor is already servicing a high priority device, and the low priority device requested for an interrupt, that will be either rejected, or their device has to wait for the processor to complete an execution with the high priority device. Thank you, and see you in our next lecture.